Over 100 years ago, Max Planck suggested that particles which had subatomic dimensions would have discrete quantities. They would not act like fluids. 5 years later, Einstein built upon that, saying that electromagnetic radiation did not have a fluid-like property, but existed in distinct units which he called photons, saying that the energy of a photon was equal to a constant times the frequency. It is this constant with the symbol h in the equation that we now call Planck's constant. Extending this further still, Niels Bohr explained the interaction between electrons within an atom and electromagnetic radiation. He explained that each electron within an atom existed in a discrete energy level. In falling to a lower energy level, it would emit a distinctive and distinct photon of electromagnetic radiation. If electromagnetic radiation of this same frequency impinges upon the atom, then the same electron may be promoted from one energy level to the next. The interactions between electrons and photons are reversible. It is this last idea that we'll use as we attempt to measure Planck's constant. We're going to use a light-emitting diode. Like all other diodes, it has a p-n junction, where a potential difference can cause a flow of electrons across the junction. In the case of light-emitting diodes, the potential difference needed to combine an electron with a hole is sufficiently high to produce a pulse of electromagnetic radiation within the visible spectrum. To manufacture the diode, a chip of semiconducting material is doped at each end with impurities. A conventional current flows easily from the P side to the N side, but not in the reverse direction. The arrow in the symbol shows the direction of possible flow of conventional current. Charge carriers, both electrons and holes, flow into the junction. When an electron meets a hole, it falls to a lower energy level and releases energy in the form of electromagnetic radiation, a photon. The wavelength of that light, which we see as a particular color, depends upon the size of that energy change. If we assume that all of the energy supplied by the potential difference to each pair of charge carriers becomes one photon of light, then by using the smallest potential difference that causes light to be emitted, and by measuring the wavelength of the light emitted, we can evaluate Planck's constant. The energy supplied to a charge is equal to the value of that charge times the potential difference. Using Einstein's relationship, that's equal to hf, where f is the frequency of the radiation emitted, and h is Planck's constant. The frequency of electromagnetic radiation is equal to the velocity of the wave divided by the wavelength. And so we end up with a final expression that EV equals hc over lambda. To make these measurements on a light-emitting diode, we'll use a circuit being drawn out very quickly and rather untidily here. A potentiometer connected in series with a 9-volt battery will deliver a variable potential difference to the diode. The potential difference across the diode is measured with a voltmeter. Overlaying the components onto this circuit, again rather untidily, you can see how it's set up. The diode is an extremely small component, and as it's laid out here, it will be difficult to see against the other equipment. So whilst we're taking the measurements, the diode will be held in front of the meter scale. We will gradually reduce the potential difference from a relatively high level until we see the diode go out, and then mark that potential difference. On this occasion, I estimate that it is at 1.74 volts. Taking a second measurement, if we watch very closely, both diode and voltmeter, on this occasion I think that the threshold was 1.73 volts. As you can see, this is not a very exact method. Going back to our previous equations, we're going to pick out the part where energy is EV and is equal to hc over lambda. If we then rearrange that, we have Planck's constant h equals ev lambda over c, where E is the charge on the electron, V is the potential difference across the diode, lambda is the wavelength of the light emitted, and c is the speed of light. The value of lambda, the wavelength of the light emitted, had to be measured using a diffraction grating. That process is explained in a previous video. And the value which we obtained, which we're going to use, is 7.14 times 10 to the minus 7 meters. The other values here are 1.6 times 10 to the minus 19 coulombs for the charge on an electron, and the 1.73 volts that we measured on the voltmeter. The speed of electromagnetic radiation, 3 times 10 to the 8 meters per second. This evaluates to 6.58 times 10 to the minus 34 joule seconds, which is amazingly close to the generally accepted value of 6.63 times 10 to the minus 34, an accuracy obtained more by luck than experimental quality. However, despite the limitations of the method, it provides a reasonable first estimate. Thank you for watching.